we covered in the last lecture series. Now today we will discuss very important topic that is also a counterpart of Z transform, and it is defined as Laplace transform. Laplace transform are the continuous time counterpart of the Z transform for the continuous time signals, and they have the same relationship with the CTFT as the Z transform had with DTFT. जो रिलेशन DTFT का Z ट्रांसफॉर्म के साथ था, वही रिलेशन CTFT का Laplace ट्रांसफॉर्म के साथ होता है. The Fourier transform and the Laplace transforms are operations that convert the time domain functions ft or xt to the frequency domain function x omega or f omega, and we call them fs in the Laplace transform respectively. The Laplace transform of a signal xt is defined by the function is Laplace transform of ft or xt, and it is defined as xt when goes to Laplace transform. The answer is x of s. The Laplace transform gives the total solution. It is a very important point here. The Laplace transform gives the total solution to the differential equations, and it is a very powerful tool in the system analysis and design. This transform is widely used for describing continuous circuits and systems, as we have already discussed in our examples of problems of Fourier transforms, that how a electrical circuit can be solved using CTFT. The same applications can also be solved by the help of Laplace transforms. And here it is a very important point is given here, that the Laplace transform has a solution to the total solution to the differential equation. We have already seen that the total solution equals the particular solution and the homogeneous solution at the time of linear time invariant system. We have discussed linear constant coefficient differential equation as well as linear constant coefficient difference equations, and we have discussed the solution of LCCDE by the help of homogeneous solution and the particular solution. Now the same solution of linear constant coefficient differential equation can also be calculated by the help of Laplace transform, and we'll see how it is solved by the help of Laplace transform in this topic. This is a very important topic, and a question may come to how a linear constant coefficient differential equation can be solved by the help of Laplace transform. Then we can see that they are again of two types. As Z transform are of two types, Laplace transform are also of two types: two-sided, that is bilateral Laplace transform, and one-sided, that is unilateral Laplace transform. The Laplace transform of a general signal xt is defined as x of s integral minus infinite. It is equals to integral minus infinite to infinite xt e raised to minus of st dt. The formula is x of s is equals to integral minus infinite to plus infinite xt e raised to minus of st dt, where s is equals to sigma plus j omega. It is a complex variable in the s plane. The sigma is defined as the real part of sigma s, and omega is defined as the imaginary part. What is unilateral Laplace transform? The Laplace transform defined to the positive time function is called the single-sided or unilateral because it does not depend on the negative values of t. That is x of s when defined from 0 to infinity, then it is known as unilateral Laplace transform or one-sided Laplace transform, and the function is same xt e raised to minus of st dt. Now in terms of sigma and omega, the function of equation number 1 can be defined as x is equals x of instead of s we are using s is equals to sigma plus j omega. So it is x of sigma plus j omega. It is equals to integral minus infinite to plus infinite xt e raised to minus of s. Instead of s we are using sigma plus j omega t dt. On taking the real part and the imaginary parts other side by side, we have this equation in the form of integral minus infinite to plus infinite xt e raised to minus of sigma t is the real part of s, and e raised to minus of j omega t, the imaginary part is taken separately, dt. Now from equation number 3 we see that x of sigma plus j omega is the Fourier transform of the sequence xt. It is basically the Fourier transform of the signal xt multiplied by a real exponential e raised to minus of sigma t. That is x of sigma plus j omega, that is x of s, is basically Fourier transform of xt multiplied by a real exponential e raised to minus of sigma t. Now when sigma is equals to 0 in this exponential term, when sigma is equals to 0, this is basically e raised to minus of sigma t will become 1, and this is basically Fourier transform of xt. That is when s is equals to only j omega, that is sigma is equals to 0, is then x of s is basically x of j omega, because sigma is 0 here, and it is equals to integral minus infinite to plus infinite xt e raised to minus of j omega t. This is basically what this is the basic function of, or this basic formula of CTFT. Now Laplace transform can be reduced to CTFT when in the case when s is equals to only j omega, that is sigma is kept 0. When sigma is equals to 0, the Laplace transform becomes equals to the Fourier transform CTFT. The Laplace transform reduces to the Fourier transform CTFT of xt when sigma is equals to 0. Now here a term is to be defined here, that is what is region of convergence. We have already covered region of convergence in Z transform. The same terminology is used here. The range of values of S for which the integral in equation number 1, the basic calculation formula of Laplace transform, that is equation number 1, converges to a finite value is known as region of convergence. That is, region of convergence consists of only those values of S for which the Fourier transform xt e raised to minus of sigma t gives a finite result or finite value. The ROC of the Laplace transform can be defined on the S plane in this way. This is the real part of S and this is the imaginary part of S, and this is the total S plane. Let us take an example. Xt is equals to ut, that is 1 for values of t from 0 to infinity, and 0 are the negative values of t. That formula is very simple. Integral minus infinite to plus infinite xt e raised to minus of st dt. That will be defined now from 0 to infinity. The value is 1 e raised to minus of st. Using the integration formula, the answer is very simple. The answer is 1 upon s, that is 1 upon sigma plus j omega. The ROC is defined for this case. The real part of s should be greater than equals to 0. Now again, xt is equals to e raised to minus of at ut. The Laplace transform formula is integral. Since ut is defined here, it will be defined from 0 to infinity. Xt e raised to minus of st dt. Xt is e raised to minus of at in this case. That will be defined in this case is e raised to minus of s plus at dt. The formula, taking the integration formula, the result in this case will be 1 upon s plus a. That is, for xt is equals to e raised to minus of at ut, the Laplace transform formula is 1 upon s plus a. The ROC in this case is very simple. Real part of s plus a should be greater than equals to 0. That means sigma plus a should be greater than equals to 0. The sigma plus a is greater than 0 gives us a result that sigma should be greater than equals to minus a. This is the way we define the ROC in this case. That is, sigma real part should be greater than equals to minus a in this case. This is the ROC for the case when xt is equals to e raised to minus of at ut. Similar case, xt is equals to minus of e raised to minus of at u minus t. Taking the limits in the same way, the answer in this case, when you solve this question in this way, from minus infinite to 0, since it is defined for u minus t, it will be e raised to minus of s plus at. The final answer in this case, after using the integration formula, limit integration formula, the answer in this case is also 1 upon s plus a. This means that this shows that two very different signals can have the identical algebraic expression for the Laplace transform, and they can only be identified only by their ROC. Now in this case, is real part of s plus a should be less than 0, since u of minus t is defined here. That means the ROC is defined as real part of s plus a should be less than 0. In this case, the ROC is defined as sigma should be less than minus a. This is the ROC in this case. So total ROC is different in this case as compared to the previous case. In the previous case, ROC was sigma should be greater than minus a. It was on this side, and in this case, sigma is less than minus a, and the ROC is defined like this. Now two very different signals can have the same algebraic expression for the Laplace transform, and they can be identified only by the help of their ROC. That's why ROC is very, very important. Again, a question is here: xt is equals to 3 e raised to minus of 2t ut minus of 2 e raised to minus of t ut. Clearly, in this case, the Laplace transform is equals to 3 upon s plus 2, and in this case, it is 2 upon s plus 1. And the ROC in this case, the real part of s plus 2 should be greater than 0. Since ut is defined in both the cases, then in this case, real part of s plus 1 should be greater than 0. So ROC in the first case is sigma should be greater than minus 2, and ROC in this case, sigma should be greater than minus 1. What is the common area in this case? Common area is this one. ROC is greater than minus 1. So the common area is defined as the common ROC for both the cases when you are taking both the cases in a single signal. So ROC in this case is sigma should be greater than equals to minus 1. Another case of cos omega naught t using the expansion in the exponential form, the result in this case is when xt is equals to cos omega naught t, the result is s upon s square plus omega naught square. The function is very simple, and the ROC in this case, the real part of s should be greater than 0, that is sigma should be greater than 0. Similarly, when xt is equals to sin omega naught t ut, the transform formula is x of s is omega naught upon s square plus omega naught square. And this is a very simple formula. You should remember these formulas. When xt is equals to cos omega naught t, the Laplace transform formula is s upon s square plus omega naught square, and the ROC is omega s should be greater than equals to 0, should be greater than 0. And when xt is equals to sin omega naught t ut, ut should be very important here. It is, since ut is defined, that's why it is taken on the positive side. Real part of I should be greater than 0, and in this case sigma is greater than 0. Again sigma is greater than 0 in this case also, and the formula is Laplace transform of xt when xt is equals to sin omega naught t ut. It is omega naught upon s square plus omega naught square. So this is the way you can calculate Laplace transform. This is the basic Laplace transform theory.